to finalize the dopant profile, and for this case, for the base, the pre-deposition and drive-in for the base and emitter has to be exercised for this base dopant, so that the final diffusion length should be summation of all those diffusion processes. And for the emitters, we just have pre-deposition and drive-in if we have a drive-in. And so we use the complementary error functions and the Gaussian profile to determine the profiles of the dopants, and so we set the junction depth where the two different dopant atoms, the amount of dopant atoms, concentration of dopant atoms are equal. Let's just discuss about the evaluation of diffusion layers. And if we have a square and everything else is masked with the silicon oxide, for example, and if we have a square L, length L, width W like this, and the top view and the side view is the junction depth is T here, then what you do is, this is a 4-point probe method, okay? We use outermost two probes, we apply the current, and then in between we have two probes to measure the voltage drop. That's the IR drop, okay? And with the proper assumptions, and that assumption should be like in this drawing, if we can assume that the S is sufficiently small, S is sufficiently smaller than the that's a physical probe. Oh, okay. That is not T. The junction depth we are talking about is sufficiently smaller than the physical dimensions of the probes. Okay. That should be assumed first. And then secondly, the lateral dimension of a wafer, lateral dimensions of the wafer, if it is sufficiently large, then the S, the physical dimension of the probe distance, then we can see the measured resistance is going to be like this. Well, these are those two assumptions is basically related to the Poisson's equations, the distribution of the electric field, and with that assumptions we can just simply get here the sheet resistance of the layer, something like this. Now, the resistance is related to the resistivity in this equation, and then now the resistivity over the thickness, we define that as a sheet resistance. Then this resistance that we can measure is related to the sheet resistance with this the geometry, right? And if we make the pattern to be L is equal to W, then this resistance that we measure is going to be the resistance is exactly the same to the sheet resistance, okay? And this sheet resistance is usually used for in the industry, and we call this square resistance, like 5 ohm per square and 200 ohm per square. That is a typical number for the bipolar transistors and so forth, okay? And that is some misprint, but that is ASR, automated spreading resistance. We use this machine, and basically what it does is that if we have M plus and P minus and M minus bipolars, things like that, and then we want to measure the resistance along the depth like this. For this, what we do is we call this the beveling. We have some with some angle, we polish that so that we moving the 4.4 from here along these directions, and then we convert that to the resistance with the distance, okay? So this beveling is just to make is just to extend the junction's distance with some angle, okay, so that we can increase the resolution of the measurements. That's what is going to be done in the actual practice. Okay. Here is the important equations that you have to notice. The average sheet resistance is related to the junction depth. Like average sheet resistance is going to be 1 over average conductivity, and that is 4.53 V, the voltage that we apply, and then the current, and Xj, ohm centimeter. This is a very useful equations. Okay, that is after the Poisson's equations, solving the Poisson's equations, we can have that equation, and that really relates the parameters that you can measure with the resistivity and conductivity of the material, of the junctions, okay? And that conductivity is, of course, the number of dopants and the mobility here, and the charges, okay, with these equations. So to characterize the impurity profile, what we are doing is, firstly, we measure the sheet resistance with the patterns making the L is equal to W. Then we can measure the sheet resistance and measure the junction depth with the spreading resistance, that the 4-point probe with the beveling. Then we can measure the junction depth, right? And then the average conductivity can be calculated with these two parameters. Sigma is 1 over rho s and xj, okay? And then with this average conductivity, we can get the surface concentration from the Owens plot. And these Owens plots are available and in the note. And then that Owens plot is is a relationship between the surface concentration and the average conductivity. So we measure the average conductivity in this fashion, and then we related that to the surface concentration through the Owens plot. Okay? So let's see. We just have examples of Owens plot, how we related the average conductivity to the surface concentration things. And here is the example, simple example. So let me just give you the first example, and then next week we continue on this second example. The first example just says that if we perform the base diffusion on the 10 to the 15th doped substrate, that should be okay. And the sheet resistance has been measured to be 200 ohm per square, and the junction depth is to be turned out to be 3 micron. And in that case, we can calculate the average sheet resistance, which is 16.7 ohm per square. And then from the Owens plot, we can determine the surface concentration, and that turns out to be 4 times 10 to the 18th. Then we can determine the dopant profile, like the surface resistance is obtained from the Owens plot 4 times the 10 to the 18th, and the base dopant level is 10 to the 15th, and this dopant becomes, along this profile, the concentration becomes the 10 to the 15th, then that's where we have junctions, okay? And that junction has been measured to be 3 microns. So this is the total profile that we have after the doping process on the silicon wafer, right? And that's pretty simple. And example 2, we are going to discuss about the example 2 in next week on Monday, okay?